Hello. Okay, section 2.2. Let's see, what is it called? More proof methods. So there's all different kinds of ways you can prove things, right? The first one we're going to talk about is a proof by contradiction. So the idea is, well, illustrated here, but essentially, if you're trying to establish like P implies Q, right? One way of establishing that is to assume that Q is not true and then deriving a contradiction. A contradiction is, I guess, of this form, R and not R, right? So that would be a contradiction. You can't have something. See, that is a contradiction. R and not R, that's a contradiction. Okay, so let's look at some examples here. Okay, give a proof by contradiction of the following statement. Okay, so here it is. For n, an element of the integers, if n squared is even, then n is even. Okay, so if we wanted to prove this statement by contradiction, we would assume that the conclusion is false, and that is, let's assume that n is odd. Okay, and we're going to try to get a contradiction. So we're assuming n is odd, but we're also assuming n squared is even. So those are our two things that we're assuming are true. So what do we do? Well, okay, you just use it. So if n is odd, that means that, as we know, that n is this 2k plus 1 for some k. Well, then let's calculate n squared. N squared is then that number squared, but we know how to multiply that. So we get this, which is that. So what does that mean? That is an illustration. We have 2 times some number plus 1. That means that n squared is odd. But we're assuming that n squared is even. So there we have both n squared being even and n squared being odd. That is a contradiction. So therefore, it must be that n is even. Okay. Let's do another one here. Give a proof by contradiction of the following statement. So for any real numbers x and y, if x plus y is greater than 2, then either x is greater than or equal to 1 or y is greater than or equal to 1. So here's our conclusion that we want to assume is false to proceed by proof by contradiction. So the way this is false is that x is less than 1 and y is less than 1. Okay? Well then, let's see. If you go up here and you take 2, now here we go. So if you take x is less than 1 and y is less than 1, right? Then if we add, add x plus y, that's less than 1 plus 1, right? Which is equal to 2. Okay, but our assumption here is that x plus y is bigger than or equal to 2. So you see that being true and that being true, that's contradictory. So that's enough to prove our assertion that if x plus y is greater than or equal to 2, then either x is greater than or equal to 1 or y is greater than or equal to 1. Let's do another example. Let's prove that the square root of 2 is irrational, okay, using a proof by contradiction. So if we're going to prove this by contradiction, we would then have to assume that the square root of 2 is a rational number. Okay, so there we go. So here it is. So if the square root of 2 is rational, now this is my argument, right? So if the square root of 2 is rational, then there exist integers p and q such that the square root of 2 would have to be p divided by q. Now, what we want to do is we assume that p over q is in lowest terms. So that, what does this mean? So that p and q, they are both not even. Because if they were both even, we would then cancel out, right, the 2's in either the numerator or denominator and make a new fraction, which would be, p1 over q1, where they're not both even, okay? So So now, but if I square the square root of 2, which is equal to p over q, this gives that 2 is equal to p squared over q squared. Oh, well, watch this. Then if I multiply both sides by q squared, I get this equation. Now, let's look at that equation. So we have 2 times q squared equals p squared. Now, if we were to look very closely at the prime factorizations of p and q, you would notice that there must be a 2 in the prime factorization of p. Okay? And therefore, that makes p squared even, because you'd have a 2 number. There's a 2 right there. That's even. Well, basically, I guess I'm making this into a big deal, but 2 times some number is p squared. That means p squared is even. Okay, so what does that mean? So this example, let's see, what is this? Tells us that p is even. Okay, let's think about that. Well, let's see. If p squared is even, then I guess we'd have to look at how could there, since the prime factorization of p is the same, we would have to see that a 2 would occur on both sides of the p. So there's actually a 4 in there somewhere, right? So that means that p would be even. Okay, well, therefore, let's see, what does that mean? If p is even, therefore there exists an integer k such that p is equal to 2 times k. So if I substitute p equals 2 times k into this expression here, that gives that 2q squared is 2k squared, and that's 4 times k squared. Canceling 2 gives q squared is equal to 2k squared. Therefore, q squared is even. Aha. That means that q is even. Thus, p and q are both even. But that's a contradiction, because up here we started with both of them, not both of them, well, where's that? We started by saying that they are not both even. Well, since we arrived at a contradiction, that means that the square root of 2, in fact, is an irrational number. Okay, now you can read about proof by contrapositive and all this stuff. I just don't want to get into it. It's fine. It's really a variation of proof by contradiction in my mind. Then here's a proof by cases. So let's look at this here. So here's a good example. Let's go through this one. They want us to prove that if 2m squared plus 3n squared equals 40, they want to prove that that has no solutions in positive integers. Okay? Well, all right. So this one cries out for us to look at, to exhaust all possibilities, because, I mean, how many m's and n's satisfy that, right? So if you make a little chart here, there's a nice proof right here. Make a little chart here. We've got m, n, right? And what's this? What is this table? Oh, entries in the table are values of, so then what you do is you take 2m squared plus 3n squared for these indicated values of m and n. Well, in other words, for this one we get 5, because if I take 2 times 1 plus 3 is 5. There we get 11. So you just go through in this example, and what you notice is that no matter what you choose, you never come up with 40. Okay? And eventually you can see if I go any larger than 3, then you're going to get, you'll get numbers way larger than 40. So that's an example of where you just exhaust all of the cases. Okay? All right, so let's see. I think that's, one last thing in this section is to prove equivalence. Okay, so the example would be this. Prove that for every integer n is odd if and only if. So this idea of if and only if. It's really if and only if is logically equivalent to P implies Q, and Q implies P. So to prove an if and only if statement, we have to start and prove that. For this example, we'd prove that if n is odd, then we prove that n minus 1 is even. Well, it's pretty clear, okay? But then we have to also prove that if n minus 1 is even, then n is odd. And that's, I can't even barely write that down, but here's a proof of that. So look at it. If n is 2k plus 1 for some k, now n minus 1 is 2k plus 1 minus 1. That's 2k. So there you go. It's even. Okay. And then the next part, we would have to start with if n minus 1 is even, then you get n minus 1 is that. N minus 1 is equal to 2k, right? So then now you just solve for n, and you get, therefore, n is odd. Okay. So that's the idea of the if and only if proof, that you have to prove two. You get to prove it in both directions. So, okay, I think that's enough to get you through most of it, except, well, let's do this existence part. So if somebody came up to you and said, prove there exists something, that means you literally have to display that there exists. Like, here's a good example. Let A and B be real numbers with A less than B. Prove there exists a number x satisfying well, A is less than x is less than b. Well, that's pretty clearly, if you take basically the average of these two numbers, it's going to be in there, right? So here's the proof. It suffices to find one real number, because it says prove that there exists, right? One real number, x satisfying that, and there it is, right? So one halfway between A and B. So that's an existence proof, right? Here's another one. Let's let I think this is, I just have it. Let's take a look at this one. Let A equal to this average, it looks like the average of these Sn, be the average of the real numbers S1 through Sn. Prove that there exists an I such that S of I is greater than or equal to A. So one of these numbers up here has to be bigger than this A. Okay. Okay, so this is a great, you really can't get your handle on it to do it directly. So this one, I think, screams out proof by contradiction, right? I mean, to me it does. I would say, well, okay, if we're trying to prove that there exists an I such that Si is greater than or equal to A, why don't we just assume the opposite of that? Let's assume they're all less than A. Well, if they're all less than A, let's see what that means. Oh, here. So if they're all less than A, right? Then we have, when we add them all together, that's less than n times A, right? And now just divide both sides by n. N is a positive number. And then you would get this average divided by n is less than A. But that's wrong. That's a contradiction, because our assumption is that A is actually equal to that quantity right here. So there's how you can, when you're trying to prove the existence, sometimes you use contradiction, you use different types of proofs depending upon the situation, and you'll get the hang of this. You need to do a number of proofs for a long, long time before you become kind of an expert at it. But there are plenty of problems in section 2.2 that'll keep you thinking. All right, thank you. I hope that helps.